On behalf of Cambridge Innovation Institute's Global Web Symposia series and our sponsor, Burning Rock, I'd like to welcome you to Dawn of a New Era, ctDNA-based biomarker detection for cancer diagnosis, response monitoring, and minimal residual disease. My name is Elizabeth Lamb, and I'm the host and moderator for today's webinar. Now, I would like to introduce our presenters for today. First is Rick Chu, PhD, Senior Director, Translational Medicine with Cogent Biosciences. Our second presenter is Joe Zhang, PhD, Chief Technology Officer, Burning Rock. Welcome, Dr. Zhang and Dr. Xu. The webinar is yours.
Hello, good morning, everyone, or good evening, depending on where you are. Okay, thank you, Elizabeth. Thank you very much for the nice introduction, and thanks to Burning Rock for sponsoring today's webinar. My name is Rick Chu. I currently serve as the Senior Director at Cogent Biosciences, which is headquartered in Boston, Massachusetts, and our research site is in Boulder, Colorado. Cogent Biosciences is focused on precision medicine. So we have active clinical development from both phase 1, 2, and phase 3 for targeted therapy. And we also have early projects for targeting FGFR and HER2. As you know, that these are all precision medicine-based programs. So myself, I was with Sanofi for 21 years before I moved to Louisiana, which was Henry USA oversee ex-China operation. And I was also the precision medicine head for Louisiana before I joined Cogent Biosciences. I would like to say that I don't have any financial connection with Burning Rock, but I did recognize that through our research project and the need, I recognize that realize that Burning Rock is one of the leader in the NGS field, particularly for the biomarker detection in clinical applications. And they have one of the significant advantage, which is they have operation in both mainland China and in U.S. That's one of the reasons that I get to know Burning Rock when I was at Henry USA. So today's webinar, I will share my knowledge and experience in the field of liquid biopsy. That's the focus. So the webinar has three sessions. One is a little background of a liquid biopsy-based biomarker detection. And then secondly, we will focus on NGS for cDNA testing in clinical trials. This is my daily practice. And then at the end, we will discuss a little bit about technical challenges and the need for standardization of NGS-based cDNA testing. So as you know that the liquid biopsy-based biomarker detecting has not been around for too long, and even though a blood sample is the most used biological sample in both clinical practice and in clinical trial study. And not to mention that, you can take a blood sample to do the PK, PD, and if it's for biological drug discovery, you can do the ADA and all sorts of antibody, cytokine, chemokine analysis. But recently it has been evolved that the circulation tumor DNA has become a focus. I want to give a little definition of the cDNA, the difference between cDNA and the cfDNA. The cfDNA is a small DNA fragment in circulation. It mostly came from the blood sample, blood cells, and after cell death, it got released into the bloodstream. And the fragment is a little bit longer than the so-called ctDNA, circulating tumor DNA, which is the fragment is around 143 to 145 base pair. And one important feature of the ctDNA is that the half-life, it has a very short half-life. It's about 2 hours. So it's a very dynamic. So it reflects, the real time of, the cancer status in any given time. And for ctDNA, there are three areas we can measure. One is the mutation in the ctDNA because it came from the cancer cell. And most of the cancer cells are driven by mutations. So we can use the ctDNA to know the mutation status. And secondly, it's the copy number of certain mutations, cancer genes. And so this is another very important information. And lastly, this is a relatively new, the methylation status of the ctDNA. This is another area that are being explored recently. The next slide, this slide shows you a little background of the cDNA-based liquid biopsy development. You can see that the molecular biology started in the 70s. But the cDNA goes all the way back to late 40s and early 50s. Before that, we didn't, have any PCR, not even, Sanger sequencing at that time. So it was mostly relying on immunological measures. People developed antibody against DNA. So they were able to measure, the cDNA in bloodstream. And you can see that, most of the events for the cDNA development is for the oncology application, especially, in recent years, there's a huge amount of advancement in both, driven by PCR and particularly since year 2000, driven by NGS technology. I think there's this slide just show you there are different technologies can be used for cDNA test. One is this real-time PCR, and we're all familiar with. And there's a more advanced, PCR, the digital PCR, and it offers a higher limit of detection than the regular PCR. And then it's the NGS. And the NGS even offer higher sensitivity and a bigger dynamic range. In terms of, the performance, if you want to know the mutation status with both the real-time PCR and the digital PCR, you have to rely on the probe. Whichever, the probe covers a specific fragment, that's all the mutation you can detect. And then from this PCR result, you can find the mutation. However, if the mutation is outside of your probe covered range, then you are not able to know the mutation status. For NGS, it does not have this limitation. It covers any mutation that if you are interested. And so this is a significant advantage offered by NGS for ctDNA based test. This is a slide show a couple of examples that how NGS outperforms the PCR method for ctDNA test. This is Aurora 3 clinical trial. You can see that this trial compared the NGS with the digital PCR and the cobas. This is a Roche product, and this is published in year 2020, and so you can see that they compared the sensitivity, and in this case, NGS showed a much better sensitivity compared to the PCR-based method. There's another ADALOS study for non-small cell lung cancer. It also compared the NGS with the other PCR method. And I believe this study was done using the Burning Rock NGS platform. And it showed that the NGS showed a better concordance and a very good sensitivity compared to other PCR-based methods. This is a kind of evolving, the emerging of NGS for liquid biopsy application in oncology. You can see that it's not too, only started in year 2014 by publication from Stanford University. So they published this method for NGS sequencing for the ctDNA, use ctDNA sample. And by year 2020, there's already a couple of ctDNA-based liquid biopsy CDX approved by FDA. I look at the total approved targeted therapy this morning. There's about more than 20 ctDNA-based liquid biopsy testing approved now, and there's still more to come. And this is the Guardant also has test approved by the NY State. This is the most stringent clear test available. So this field has been, developed very rapidly, and we actually, when we perform a clinical trial, whenever possible, now they would, consider ctDNA sample collection to incorporate into our clinical study. So this, I'm going to in this session, I'm going to cover the NGS for ctDNA testing in clinical trial. This is what basically is what I do on a daily basis. So this cartoon shows you, the ctDNA application in different stages. For early cancer detection, which is, very important to know if there's any mutagenesis or any cancer exists in early stage, so you can inform the patient early on for necessary therapy or treatment. And secondly, the other very important application is surveillance for the so-called microstatic disease, or MRD, which means you have to monitor, the development of the disease, whether, the disease get, improved or getting worse. And sometimes, the molecule level is so low, so it's called the minimum disease, residual disease. You have to monitor and keep the surveillance of the disease progression. And thirdly, this is a relatively easy, you take the patient sample, collect the plasma, extract cDNA, and use this information to select the patient and decide the stratification in our clinical trial. So those are the three main areas for liquid biopsy test in clinical study. This gives you a example, how the ctDNA compared to the traditional tissue-based enrollment. What are the advantage and disadvantage? For example, this is a Japanese group published paper in Nature Medicine. You can see that they used 5,621 samples from tissue. And the success rate was about 90% because the 10% of tissue did not generate, sufficient information for enrollment. Whereas, for 1,687 cDNA samples, the success rate was 99% because this sample is more homogeneous. So, often you have better chance to get a definitive result. So this is a success rate for the enrollment. And if you look at the time it took for the tissue sample, the median time is 19 days, and it could, between 14 to 90 days. Whereas for the ctDNA, it took less time in this particular study. I think that's a standard practice. Usually, it's 2 weeks is a reasonable time for both, tissue sample and a blood sample. But always, blood sample has this advantage. You don't need comprehensive, pre-treatment. Sometimes the tissue sample needed to do a micro dissect to get the sample you needed, whereas the blood sample, you don't need to do that. And in terms of the objective response, there actually, the graph shows some difference, but it's a 16% versus 20%. And if you look at the PSF, it's very similar regardless of which way you enroll the patient. So this shows you, some, advantage of using ctDNA as a mean for enrollment. It's basically, easier to handle. And there's another study, it's called a PERFORM study, and I use, you can see that this is also a huge study. And they enrolled 2,792 samples based on tissue, and the success rate was 69%. So there's almost 30% of the sample did not generate a satisfactory result. Whereas for the ctDNA-based sample, the success rate is much higher, 81%. And in terms of concordance between the tissue and the blood, you can see that the positive concordance is 81%. Basically, if so the positive agreement is 81. However, the negative sample agreement is much higher, 92%. Basically, if you have a negative result in tissue, and it's likely, it will be negative in by the blood sample. And also, the response rate between the tissue enrolled patient and a liquid biopsy enrolled patient are very similar. And this shows you the slide show you the cDNA profiling user NGS has the greatest sensitivity and specificity. You can see this is one of the example published, I believe the leading authors from Canada. And this is a late stage non-small cell lung cancer. You can see that, the the sensitivity is great, but it depends on what the specific mutation you look at. There's, some differences among, the different mutants, but the specificity is always, great. So basically, you don't get, the wrong information by using, the cDNA sample. This is data published use the Burning Rock platform, and you can. This is a multi-gene panel study. You can see this is a 40 sample paired sample between tissue and a blood sample. You can see that the agreement, which is the matched between the tumor tissue sample and the blood sample result are very, very high, and there's only few samples that you detect mutant only in the tissue, not in the blood sample. Well, there's also I think a couple of patients detected the mutation only in the blood, but not ctDNA, but not in the tissue. So the bivariant sensitivity is 87%, and particularly for the oncogenic driver mutations, the sensitivity is even greater, 96%. This is another publication from Burning Rock. You can see that this is a tissue-based MSI high and a plasma-based MSI high, and these are in a very good agreement. Whereas the MSI tissue MSS and MSS in plasma, they're also agreed quite well. And there's a smaller population that in tissue MSI high, but in plasma it's MS low. And here give you a assessment that the so-called positive predictive value is 100%, and whereas a negative predictive value is 98%. I try to keep my time. So this is another very important area of so-called blood tumor blood TMB. So this is nowadays it's a very important comprehensive biomarker for the immunotherapy. And you can see, in this case, the TMB high has a much better response as a response to the anti-PD-1 treatment. And this is the overall survival also show a big difference in the TMB high group versus the TMB low group. And cDNA, the blood-based TMB testing is, very, very efficient compared to the tissue-based NGS or tissue-based IHC method. And this is for the co-mutation test. Obviously, in this case, because you run NGS, you're not just detect one mutation, but you can detect all the mutations if you want it, and it shows the response to EGFR inhibitor treatment, and this is just show the different mutation status the patient have different response. And here's another example. Actually in this case, this KEEP gene did not show the difference between the wild type and the mutant. Whereas the STK mutant and the wild type did not show, the difference for the KRAS inhibitor. So it really depends on, what the specific mutation. But it is very important to know, not just your, therapeutic target mutation, but also the other associated mutation contributed to the same pathway or related pathway that could have an impact. So NGS-based liquid biopsy provide a comprehensive information for us to make this decision. All right, I'm now running. I try to wrap up fast. And this slide just show you that the liquid biopsy provide the kind of online mutation status and particularly for this EGF receptor inhibitor type of therapy. And there's a different generations of inhibitor, and based on the mutation types, you have to select the right therapy. So this NGS-based liquid biopsy provide a useful information for us to make the right decision and based on the mutation status. And this is very important information that, for the liquid biopsy, for example, this is, early on in the baseline, the cDNA detect the same mutation as the tumor tissue. However, after the treatment, the tumor tissue is gone, and you don't detect much of, the mutation by the tumor tissue. However, the mutation can be detected in the liquid biopsy, in the ctDNA. And in the later stage, it became metastatic in the fourth cycle of treatment. And there's more mutations detected by ctDNA, but still less mutation in the tumor tissue. And here's another example which explains, because the ctDNA is from blood sample, it's kind of a combination of all the mutations that can be detected. Whereas, in tumor tissue, it depends on where you sample the tissue, and you could get a different result. So this, I think you probably have heard enough, example that the ctDNA is a good measurement of clinical response and measure the clinical efficacy. And this is also, example that, cDNA can be used for the re-challenging, enrichment. It can be used to make a, enrichment decision. I think I'm getting into the third part of MRD. I believe Dr. Zhang has a whole session cover this topic. I'm going to move to my last slide, the take-home message. Yeah, so I'm sorry, due to the time, I had to cut my talk short. The take-home message is that the cDNA now has become a crucial surrogate marker in oncology. And in our clinical trial, you cannot imagine that any trial you're not considering take blood sample and to perform a cDNA test. So this became a standard of practice in our in design our clinical trial, whether it's a baseline sample or on treatment or post-treatment sampling. And there's some technical challenges as a sponsor, as drug development company. I think our job is to select the right vendor, such as Burning Rock. Obviously in U.S. there's other excellent companies that you can choose, and you can build the relationship and incorporate their platform into your clinical practice. That's all I have. I'm sorry for taking a longer time, and Dr. Zhang, now it's yours.
Okay, great. Yeah, thanks, Dr. Chu, and and also thanks and the host, and actually I'm the Chief Technology Officer of Burning Rock. My name is Joe Zhang, and I'm currently based in China and Shanghai, China. So it is my great honor to present here, try to represent Burning Rock to give you some kind of a introduction of a new MRD assay. We call it BR Profit, which is a personalized approach MRD assay for solid tumor. So before we move into the topic, so let's just give you guys a little bit of brief introduction about Burning Rock, since I think Dr. Chu already. So Burning Rock actually is a global company, and it's being established in China, but right now it has also a U.S. site in Irvine, California. So basically, it's a company focusing on next generation sequencing and diagnostic for oncology. And we actually serve a lot of diagnosis assay for cancer patients. We also develop in the early detection assay. Meanwhile, we also provide a lot of pharmaceutical research and opportunity for collaboration. So there's a lot of numbers showing here. I don't want to read it again. Basically, it's just showing the Burning Rock Diagnostic. DX is a leading diagnosis company focusing on NGS oncology in China. And right now, we're actually expanding our capacity and the capability in the US as well. So let's move to today's topic for sake of time. So the first thing, and my topic will be focused on MRD. So there are three parts. The first part, I'm going to give you an introduction about the MRD's clinical utility. A second one will be the technical aspect, since my job role in Burning Rock is basically technology. So that's why I'm more focusing on technology itself. Then the third one, I'll give you some introduction about the BR Profit MRD assay, which is the MRD assay we are currently invest a lot and also trying to do a lot of clinical study on it. So the first part will be the clinical utility MRD in oncology. So minimal residual disease, aka MRD, basically it's a term usually for leukemia. Used to be. Usually that's just talking about the concept of MRD was being provide some kind of a prognostic and therapeutic assessment after achieving the CR, such as leukemia. But in the beginning, in the MRD is based on those kind of like optical observation. Then later on, it's based on the PCR and also based on the facts, all those things. But right now, we are trying to actually apply this kind of concept into a solid tumor. So that's why solid tumor MRD will become the topic we've been talking today. And the solid tumor, I think the ctDNA, the circular tumor DNA, is a very important biomarker for solid tumor. The reason is the solid tumor is not like blood tumor, blood cancer. It's basically the tumor itself usually not floating. Instead of but the cell-free DNA, the tumor-derived cell-free DNA, we call ctDNA, is floating around actually in the plasma, in the plasma. And that's why we've been looking at a lot of different kind of aspects, including the mutation as well as other epigenetics markers listed on the right. So this kind of a fragment DNA, tumor-derived, serve as a very good surrogate for us looking for whether this patient has a residual disease or not. The reason so its assumption here is basically if the patient have residual disease, the tumor will still somewhere in the body, and then it's still going to shedding the cell-free DNA or ctDNA into the bloodstream. Then if we can catch it and determine whether the fragment is coming from tumor, then we can say whether this patient is MRD positive or negative. So so that's why the ctDNA utility is being applied on different kind of aspect. The therapy selection will be the most important, the currently used clinically. But there's a lot of emerging application, including the early detection as well as minimal residual disease, and also the surveillance. So that's the thing actually we're going to focusing on today. So let me just give you some kind of introduction about the utility of the MRD assay. I think the first one will be the MRD assay. I think it's already been proven many times. It's basically provide a risk of recurrence. That's pretty much the prognosis utility. So in this case, basically after the curative treatment, for example, surgery, then the blood draw will be done, and also the ctDNA detection, we're using different kind of methodology, including the qPCR, digital PCR, and the NGS, trying to determine whether the tumor DNA is still there, like I just mentioned. So there's a lot of a case being presented. There are several examples down below. There's 3 different examples, 2 on colon cancer and 1 on breast cancer. As you can see here, basically the take-home message here, by what kind of thing, by any kind of a methodology, if the ctDNA negative, usually the percentage recurrence-free PFS or RFS basically is way better than the MRD positive patient. So you can see the KM curve. There's always been, separation, and sometimes the separation will be greater, sometimes the separation will be less. Depends on what kind of a disease stage and what kind of a patient population you've been looking at. It also depends on, like, say, what kind of a methodology you've been using. The detection sensitivity and the specificity. I'm going to talk about that later. The second utility actually very useful is using MRD to assess neoadjuvant therapy efficacy. As you know, the adjuvant therapy basically is some kind of adjuvant therapy before the surgery. So usually there's a pathological complete response assessment after the surgery to make sure to see whether the NAC, neoadjuvant therapy, has some kind of efficacy. But as you can see here, there are several examples. On the left side, there's basically using a urine capsid, which is not plasma-derived ctDNA, but it's using the urine ctDNA to look at it. It looks very similar if you look 2 different kind of a KM curve. The top one actually is using the MRD assay to determine the MRD status. Then the bottom one is using the pathological review to determine the PCR or non-PCR. As you can see here, basically the RFS, the PFS actually is very similar, actually non-inferior if you're using the UTDNA or ctDNA assay to look at it. On the right side, basically there's another breast cancer data showing there's some kind of crossover. You can see here some patient after the, even if it's a ctDNA positive, but it's still being treated, using the pathology review, going to see the non-PCR. But on the others, also there are some way around. Basically, if it's a ctDNA negative, but it will be determined as a PCR. As you can see here on the right curve, actually, there's a 3 different curve, but the interesting part here, even if the ctDNA, even it's been determined as non-PCR, which means the pathological review showing there's still some possibility of the tumor existing after under the microscope, but the ctDNA showing negative, but this kind of population actually showing same prognosis, same kind of a survival curve in terms of a distant recurrence-free survival, and similar to the all negative patient. So this is actually gives some kind of indication. So if using the ctDNA or MRD status to determine the disease prognosis would be better than just based on the classic pathological review. So the third utility basically is using MRD to predict immunotherapy efficacy. So there's 2 different kind of disease on the left hand side, which is, I think, if you've been familiar with this you kind of already know this is a very important, very popular example, basically utilizing it's on bladder cancer. Basically it's called Amvigo 010 or 10 basically. So basically this is showing like only MRD positive or aka a ctDNA positive patient can benefit from the immunotherapy. So you can see the ctDNA plus curve, there's 2 different kind of separate line there. But on the other side, and even for the non-small cell lung cancer, which is Empower 10 trial, although both, in this case, basically both immunotherapy can be beneficial for both ctDNA positive and negative. But you can see here, so basically positive side, MRD positive patient can get more benefits from the immunotherapy. The line separated better in general. The fourth utility is using MRD to guide therapy decisions. This is actually a lot of physician and company and the technologists been really looking at it. From all previous ones, usually just give you some kind of a prognosis assessment or something like just efficacy assessment. It's not related to therapy decision. In this case, everyone's looking at whether you can using the MRD status to determine what kind of treatment you can do. And that's why there's a de-escalation treatment observation or escalated treatment observation based on the MRD assay. So basically, one is look at whether the ctDNA negative can delay the treatment. That's what we call de-escalated. The other one is whether you can see, once you see the ctDNA positive in the MRD status, then you can just escalate the therapy or using some kind of novel therapy. So there's one good example showing here is basically dynamic trial, which is just published this year. So basically, it's a very famous de-escalated trial, basically showing if you look at MRD positive a negative patient population, if you do de-escalation treatment, the 3-year RFS actually showing non-inferiority compared to against the SOC. So the two lines actually next to each other is very good on this kind of stage 2 colon cancer, I guess. So basically, that's the 4 different utility. The second part, I'm gonna focusing on the ctDNA MRD technical aspect. As you can see here, there's 2 different approach in the ctDNA detection. On the left side, basically we call tumor naive or agnostic, which means you don't have any kind of knowledge on the mutation, and then you just draw a blood tube and then just test it to see whether you can see any kind of driver mutation. Usually that's just apply on the therapy selection, very, very likely. So the reason is for the late stage patient, if you cannot get tissue from that patient or you don't know where to get the patient sometimes, tissue from that patient, then you just do a liquid biopsy to see whether you can see some kind of mutation, then try to indicate whether you can use any kind of a target therapy drug. And those things actually have some kind of limitation. Basically, the limit of detection usually is not so low, usually like 0.2 to 0.5% at the most. And it's relative qualitative, which means you basically are only looking for this kind of targetable therapy, a targetable drug mutation target. And on the right side, basically, is tumor-informed or bespoke assay, which means this kind of assay, you have prior knowledge of mutation by tissue sequencing, and usually, which means you're going to do a tissue typing first. And once you got a tissue typing, then you know where you're looking at it for those kind of mutation from the ctDNA, since if you think the ctDNA is coming from that tumor originally. Then you're looking for clearance or recurrence of this kind of recurrence of this no mutation. That's why we call it MRD or surveillance. So this is basically the LOD can be as low as very, very low, like 8 ppm. The reason is I'm going to talk about the reason later, but basically that's the take home here. It's relative quantitative. So which means the informed assay usually give you a much lower LOD, and it can be used in MRD assay primarily. So the ctDNA fraction after this kind of curative therapy, for example, the surgery is very low. This is something we already know. This is a lot of publication showing here. So the take home here is different kind of cancer type after the surgery. Usually the median fraction of this kind of a ctDNA, it's 0.03%, which is a 3 times 10 to minus 5%. 5 fraction in terms of a fraction. So it's really, really low. That's why if you're just using agnostic tumor naive approach, usually it's tough, not so easy. So there's one example showing here, basically an SEQC study led by the FDA group, and actually Burning Rock joined, participate this group, and we applying on this assay, which is 160/18 assay tumor target therapy or therapy selection panel for ctDNA detection. Although Burning Rock actually showing green, showing very good sensitivity on down to like a 0.2 to 0.3%, but you still can see once the very allele frequency drops, then the detection sensitivity also drops. So that's why some conclusion being drawn in here. So if you're only doing tumor naive or tumor agnostic assay, it's not good for MRD detection. So we have to rely on the tumor informed approach to do this. So there's a lot of way to improve the detection sensitivity. Since I'm biochemistry in training, so that's why I've been looking at this kind of library prep assay for many years, even before I joined Burning Rock, since I was used to work for Illumina in San Diego, working on assay development. So in that case, we basically, there's a lot of different ways you can try to, improve the detection sensitivity. The first part will be to improve the library conversion, which means you want to harvest as many as a ctDNA, convert them into library and sequence them out. You can improve the ligation, get a more input amount into the assay as well as the sequence to saturation. The second part will be reduce noise as well, the unique molecular UMI, unique molecular identifier, or any kind of a way to improve the specificity. For example, look at the face genome, face variants usually can improve the specificity much better. The third part will be you can look at instead of one site, since you can look at the many sites. So many sites means you can monitor more mutations concurrently. This is usually advantage of NGS compared to qPCR or ddPCR. And there's some extreme case, for example, MRD detect, which is using the whole genome approach to look at across genome and to see whether you can harvest as many site information as possible. Of course, there's some kind of a cost issue there, since you need to sequence fairly deep. Even if you do whole genome, you only can sequence like 30x, 40x, already give you a lot. You still require a lot of data there. So there's a lot of different commercial ctDNA assay. I just don't want to read them again. So basically, there are 4 different approach. First thing is the plasma genotyping. Usually that's for target therapy. And the cfDNA methylation usually for early detection, and someone's using MRD assay as well. And SNV, ctDNA, MRD, that's the tumor informed, and BR profit I'm gonna introduce later on will be this assay. There's something other like a very, very low LOD, usually that's called phase variance ctDNA, MRD. Let's look at this very specific variance. But this kind of variance, usually if you want to get this kind of variance, usually you have to do a WGS, the whole genome sequencing, trying to get them out. Otherwise, it's hard to get enough this kind of variance if you're just doing a whole exome sequencing. Before I move to the next part, there's one thing I just want to point out. So even if you're talking about tumor-informed calling, there are 2 different kind of approach. First thing will be using the off-the-shelf panel, which means you have maybe several hundred genes of this kind of cancer oncology-related genes, and you keep using this kind of off-the-shelf panel we call fixed panel to detect it. Since you're using this panel, you use this panel to profile the tissue, then you know which mutation you're gonna looking at it. Then you sequence the cell-free DNA using this panel again, but you sequence fairly deep. And this is actually, there's one example like a Roche-Chavini or Capsic, there's a surveillance kit doing this kind of thing. But more popularly, we can talking about a personalized panel, which means you can, based on this person, the cancer, the tissue information, which is design a specific tiny little panel, which is only focusing on this patient, this mutation, and get a very personalized, and doing the tumor informed calling. So, for example, the most popular one will be the Natera, single Natera. And Invitae, and they incorporate Archer, they have their PCM, and Burning Rocks actually has been doing the similar thing as this way. So my third part, will be the BR profit MRD assay introduction. So very briefly, basically BR profit assay is based on rely on the whole exome sequencing tumor profiling, and we also do a lot of other things, therapy selection aspect on this whole exome sequencing. And we do a personalized panel design, and we intelligently select up to 50 tracking sites based on the tumor-wide sequencing, whole exome sequencing. And then we also will be able to add some customized content if you want. And then we performed the BR-profit MRD assay, which is a similar chemistry as like SEQC2 study, but we are doing different kind of bioinformatics. And we sequence very deep just because the panel is very, very small. That's why we can sequence like as minimal as like 100,000 X. And we do this kind of UMI error correction and the tumor fraction estimation to determine the MRD assay status. So this is basically the workflow. And so there are several things I just want to point out. The first thing, like why choose 50 sites? Since we did some kind of a data simulation, what you can see here, with different kind of color, which means different size of variants we can choose, number of variants we can choosing. And you can see here, based on the noise, basic kind of background noise as low we can achieve, and signal to noise ratio we can achieve. So basically, if you select 50 variants, you already pretty much saturated your capability. And that's why the ctDNA fraction can be as low as like 1 times 10 to 5 minus 5 level. And that's why we choose 50. And then we do this kind of variant, as I just mentioned there, if you have different kind of DNA amount input, the more DNA input usually give you higher sensitivity. So we did a different kind of input amount from 20 nanogram up to 100 nanogram. And you want to see here, the background is basically no mutation is at this level. Any kind of signal here, positive ratio means that's false positive. So as you can see here, with 20 nanogram, which is the lowest one, this data, this box showing still significant difference compared to your background. But if you do 10 to minus 6, there's still some kind of a drop off. It's hard to determine whether this group is different from this group. But definitely more input will benefit more, since you can see here the positive signal will be higher frequency if you have more input amount of DNA. This is on analytical, so I'll talk about the clinical later on. So this is basically a theoretical LOD matrix based on our observation. You can see here from different number of tracking sites and a different number of input amount of DNA. And as you can see here, in order to, since we choose 50 variants as our BR-profit setting, so usually that can reach to 10 to minus 5 level. Even if you have a very low input amount. And at this moment, we target for as low as 20 nanogram, just trying to make sure you have enough, like 4 times 10 to minus 5 LOD. There's another example, so I just don't want to spend too much time to explain this plot. So briefly, basically, it's 5 different kind of cell line mixture and cell line serial dilution. And the highest dilutions are 10 to minus 3. And the lowest dilution 8 times 10 to minus 6. As you can see here, the site-wise sensitivity, if you use only 5 times 10 to minus 3 is 100% sensitivity. This is all blue here on this cell line. And we also estimate if you using another cell line, this is a negative side, and what kind of a false positive rate it is. And what the take home here, if this number is significantly different from this number, you can think this is reliable result to determine the sample positivity. So basically, based on this number, and we did this kind of that's the sensitivity measurement on 5 different kind of cell line on GM 24384 a normal cell line background. So basically, this gives us a lot of analytical validation result showing the limit of detection. And we also doing this kind of a practice again and again, trying to look at the in order to achieve this number, what kind of if you want to get a 10 to minus 5 sensitive, LOD, how many depths of sequencing and what kind of how many number of the loci you can use, and based on that we got this result I just mentioned. Just don't want to speak too much on this. So briefly here we did another commercial available test. We designed these 50 sites across utilizing a serial care ctDNA MRD assay panel to look at it. It looks very similar to the result we achieved internally. So back to the clinical, you probably will be very interested with. So this is one example we presented in AACR early this year. Basically, that's the non-small cell lung cancer cohort. And we look at the preoperative. Since you can think about it, since preoperative means this tumor has not been removed, it should be all positive if your assay is sensitive enough. So we compare three different kind of approach: tumor agnostic, which is the least sensitive assay; then tumor informed, which is using a fixed panel, like 180 genes fixed panel to do tumor informed calling; then the profit, which means using personalized dynamic panel. As you can see, the orange bar definitely is the highest in different kind of stage, and this is actually give us a lot of confidence, saying, okay, this assay is good enough for might be is promising, trying to after to monitor the MRD status and looking for the clinical utility. So there's several other examples. We're currently doing a lot of clinical study. So this is some other example using the preoperative sensitivity to measure, to calibrate the assay. As you can see here, on different kind of organ cancer, and we can achieve very good, lung cancer actually it turns out the lung cancer is the most difficult part. For a lot of other digestive system cancer, usually you have a very good sensitivity in terms of preoperative sensitivity, even at the stage 1. And so that's why we, back to the non-small cell lung cancer study, we look at the different kind of analysis. We did a landmark analysis, and we did a longitudinal analysis for the ctDNA MRD detection, and then we bundle with the recurrence information to determine the clinical sensitivity and the specificity. So landmark analysis means like after surgery, and then we collect the blood, and to see whether this blood, if we see MRD positive, whether this patient will recur later, and trying to using that kind of ratio to measure the sensitivity. And also, if we see the negative, and out of all the patient who's not recurrent, and how many patient we got negative, that's a specificity. As you can see here for the landmark on different kind of clinical study, the lung cancer I just mentioned here has more than almost like 200 patients there, and we have very good separation of two line. And for the colorectal cancer, the 41 patient, we also have a very good HR ratio, hazard ratio. And the pancreatic is a relatively small cohort at this moment, but it's still showing very good, separation there. And the surveillance are even better, since surveillance means that you have a serial, blood collection. And you can see here for the same cohort, the lung cancer, the surveillance, the MRD negative cohort almost like reached to the ceiling and never drop. And for the gastric also almost perfect, but it's a small patient cohort. And the breast seems not very, very significant and not very impressive, I would say, but still see the separation. And then pancreasis also, but the number also pretty small. This is just all ongoing clinical study, and something is, for example, the lung cancer will be published very soon. And for the remaining patient, for the remaining cancer type, it's still ongoing collection part. So the take home here, basically, I just don't want to read it again. Basically, we introduced the prognosis, the MRD value is already demonstrated, but right now a lot of groups are looking at the guidance of treatment and for the more therapeutic utility for the MRD. And the FBR profit actually is a tumor-informed personalized MRD assay. And it has very high sensitivity and high specificity, and it already demonstrated a lot of clinical utility, at least at this moment, prognosis utility, but hopefully we can get more, in this kind of interventional study to look at the other utility and for the guidance of treatment, guidance utility in the future. So sorry for a little bit over time, and thanks for the attention. Thank you.
Thank you very much, Dr. Zhang. I fear we have run over. What I will do, any audience questions that have come in, I will forward them along to our presenters, and you'll receive those answers directly via email.
Sure.
I want to take this opportunity to thank our two presenters, Dr. Joe Zhang and Dr. Rick Xu. I'd like to thank all of you who came and attended today. I'd also like to thank Burning Rock for sponsoring today's event, and ask that all of you take care, and we hope to see you at future CII Global webinars. Thank you all again, and have a great rest of your day.
Thank you.